This problem asks us to find the magnitude and direction of the magnetic force on a conducting loop as it's pulled out of the region where there's a uniform magnetic field. First, let's talk about why there's a magnetic force, and then we'll find its direction and its magnitude. We know from Faraday's law that the induced EMF is minus the time derivative of the magnetic flux through some area. When we have a conductor, by Ohm's law, that induced EMF will equal I times R, the induced current, times the resistance. And we know that the magnetic force on a current carrying wire is I times L cross B. That force is the magnetic force that we're asked to find the magnitude and direction of. There are several ways to find the direction of this force. First, let's do it by Lenz's law. Lenz's law tells us any induced effect will oppose the cause. The cause of the induced EMF and the current, and therefore the force, is this loop being pulled to the right. So the effect, the force in this case, will oppose that. The force must be directed to the left against the motion that's causing it. So by Lenz's law, I know the force on this loop is going to end up being to the left. Let's find the magnitude and direction of this force using the expression IL cross B. The first thing we can do is replace the current I with the EMF divided by the resistance R. And then we can find the EMF using Faraday's law. For that, we need to know the magnetic flux through the loop area. The magnetic flux, phi sub B, is the integral of the magnetic field over the loop area. I'll choose the direction of the loop's area to be into the screen, in the same direction as the magnetic field, so that dot product is positive. Making this choice for the area vector A also determines the positive direction for the EMF and for the current. If we calculate the current and find it's positive, it means it'll be in the clockwise direction consistent with the right-hand rule for choosing that area vector. If we find a negative current, it'll be in the opposite direction. While we're over here, let's add some dimensions to the loop. I'll call this dimension L, and we'll call this horizontal length inside the magnetic field the distance x. Notice that x and v are in opposite directions, so this velocity v is actually minus dx dt. If we come back, we can now evaluate the magnetic flux. It equals B times the area where there's a magnetic field. That's B times L times x. To find the EMF, we take the negative time derivative of that flux. Of the three quantities there, only x varies with time, so we have BL minus dx dt, which as we saw above is v, so we get BLV. Each term in that quantity is positive, so the EMF is positive, and that tells us that the current is also in the positive direction. Given our choice of A, we see that the current is in the clockwise direction. So in the bottom leg, the current is directed to the left, which gives us an induced magnetic field, which I'll draw in orange, that goes into the screen inside the loop. In accordance with Lenz's law, that induced magnetic field is countering the decrease in the magnetic flux as the loop is withdrawn. In the vertical leg, the clockwise current will be directed up, and in the top leg of the loop it will be directed to the right. If we draw some more induced magnetic field lines, we see that they are always directed into the screen inside the loop in accordance with Lenz's law. Now that we know the directions of the currents, we can evaluate the direction of the force on each leg using IL cross B. On the bottom leg, L cross B is directed down. I'll call that force F1. On the top leg, L cross B is directed up. They have the same magnitude, so it's minus F1, and those two forces cancel each other. Only the force on this vertical leg will give us a net force. L cross B on that leg is to the left, giving us the same direction as we found in the beginning using Lenz's law. Now we can evaluate the magnitude of that force. It equals E over R times the magnitude of L cross B. L and B are perpendicular, so we just get E over R times LB. Substitute our expression for the EMF. Simplify and substitute all the numbers to find that the net force on this loop is 6.48 times 10 to the minus 3 newtons, and we know it's directed to the left.